Hey, we're live. Okay, so movie magic.
We're professionals.
We are. This is definitely gonna get cut, probably. So today's topic is development tools and debuggers. So we're gonna get into what that means, but essentially, these are the tools that you're gonna use or can use to solve problems in your code. We use code to solve problems, but sometimes the code breaks. Lots of times the code breaks, and these are the tools, more or less, that you're going to use to solve those problems that the code creates. So today's topics specifically include code analysis, which is just a concept, just an idea of under which debuggers, linters, and different testing things go under. And then we're also going to talk about virtual environments, which are a Python-related topic for isolating your code and also figuring out dependencies for your project. It's just a very useful tool, which more or less goes under this topic umbrella. And then we're also going to talk about integrated development environments. And at the end, we're going to have a little exercise, I believe. So code analysis is, I hate to say this, but it's pretty self-explanatory. It's basically the analysis of your code. And specifically, there are tools that analyze your code for you. So there's two main types. There's static analysis and dynamic analysis. And static analysis isn't super self-explanatory. Basically, what it means is it just doesn't run your code. It just looks at your code, more or less like an editor reading a paper. So it'll look for syntax errors. It'll look for whether or not your code conforms to style. So say you require that all code is indented 4 spaces instead of 8 or 2. A static analyzer would find that, or would tell you like, hey, this is indented incorrectly. If you're writing C code, it could also tell you like, hey, this doesn't have a semicolon at the end. Things will probably break. And another form of static analysis is type checkers. So if you're writing in a language that requires that you have certain types for variables, like explicit, like integer or float, a static analyzer might tell you like, hey, at this point you try to add an integer to a string or something like that. Under dynamic though, dynamic is sort of like the tool runs your code and then tells you about what's wrong with your code or right with your code. And under this, there's debuggers, memory profilers, and coverage testers. So debuggers run your code, and when things break, it'll give you like a list of like the state of your program when it broke. Memory profiling will tell you what's going on in memory when your program is running. So if you have like a memory leak, that would be detected by a memory profile. And a coverage tester tells you how much of your code is being checked by your tests.
Yeah.
So let's dive right in. So debugging is the top quote I got from Wikipedia, just like all the top quotes I get. It's essentially a computer program that is used to test and debug other programs. Super, super interesting, I know. But essentially what it does is what you already probably do when you're writing your code. It will print out broken variables or just variables in general. It'll also read and report error messages, and it'll highlight incorrect syntax when something broke. So if you're writing a script and it runs through your program and it hits a spot where something broke, the debugging module or debugging functionality will basically print out like this variable is 0 and you try to divide by it, something like that. Or you have 2 parentheses here when you should only have 1, or it might be a little more vague than that. It might say unexpected token, which just means there's something here that I wasn't expecting, like a certain character or a certain string. It does all these things that you already do, but it does them very fast and it does them very efficiently. So you could have print statements every other line, but a debugger will just tell you this broke on this line, more or less. And pretty much every popular language out there, C, JavaScript, Python, I'm not going to list them all, has some form of debugging built in or plentiful debugging tools available. Debugging is also just like a concept, not just necessarily a program. But for like C, there is GDB, which is the GNU debugger, and that is like an explicit debugging tool. But there's also other forms of like debugging, like I said, print statements. Cool. So on the CLI side, or the command line interface side, like I was just talking about, there are debugging tools. So Valgrind on the C and C++ end, end of the spectrum, is more for memory mapping, but helps you debug your program. Valgrind is the go-to tool for figuring out if your C++ or C program has memory leaks, which is super common. You're allocating memory and you're not deallocating it, and then your program starts to eat up a bunch of memory. Valgrind is very Valgrind is very specific in its use, though, whereas GDB is more general. GDB might give you some features that Valgrind gives you, but definitely not as thorough. GDB is more, you run your program, it breaks, you say, okay, print out this variable when it broke, and then it prints out the variable, and you're like, oh, obviously, that is the wrong value, or something like that.
Or I think one of the most common and useful features of GDB is for seg faults. So seg faults are very difficult to debug because you basically just get like either a stack trace, which like may or may not actually be related to why your code is seg faulting, or you just get like, hey, this seg faulted, bye. And if you run your program in GDB, it will tell you, usually with pretty high accuracy, where it's actually seg faulting, and then that makes it way easier to debug. So you might be saying, like, why would I be printing variables over the place? Like, I can just do that. But there are a lot of errors that you will get that you won't be expecting, like a seg fault, and you will have no idea why they're happening. And so GDB and also Valgrind are really helpful for things like that, or like pointer error, null exception or something where you're like, I don't even know what that means. Valgrind and GDB are great for that.
Yeah, they're really useful tools. They basically make it so you don't need to run your program, find an error, add a print statement, compile, run it again, etc. You can just compile it, run it through a debugger, and then print statements as you go. You can also step through your program line by line, which is a pretty sick way to just run through your program, because it's very easy for us to understand this line is being run, this line is being run, etc. On the Python side, there's PDB, which is Python debugger. It's just the debugger for Python. Very useful, though. And then also just built into Python is the concept of a stack trace. So here, this example is actually a stack trace where we tried to do an operation on an integer and a none type variable. So we tried to basically add 2 to none. And that's an error in Python. You're not supposed to do that. So this sort of tells you unsupported operand types. So it describes the error. And then it also tells you which lines it happened on. So line 2 in F, there's some variable F that is on line 2 that was set to the wrong thing. And then on the Node.js side, there's Node debug, which is just built into Node.js. And then there's also the Node inspector package. Again, like I said, for every single popular language, there's a debugging suite or many debugging suites. It's up to you to like go out, search for it. If you're into Ruby, you could probably just search Ruby debugging or even Rails debugging for specific Rails stuff, just as an example. Let's keep talking about Valgrind because it's pretty useful if you're doing a lot of C, which you kind of have to for school. It's a dynamic analysis tool. I actually already said most of what this says because I forget what my slides say. Yeah, and it's pretty easy to use, more or less, and it's verbose, but if you know how to read it, it's very useful. And it's not that hard to read it. If you do have difficulties, though, reading any sort of debugging tool, read the documentation, and it'll probably tell you, okay, it tells you like 1,000 things, but you only need to know like what these 3 lines say. So that's sort of a common thing. Another really useful tool is if you're doing web development in your browser is the console. So here you can inspect elements, see what your HTML elements are, but what we actually care about is the JavaScript console. So we can just type in JavaScript and it'll just run JavaScript for us. And we can also figure out, we can analyze the JavaScript that's running on the current page. So if you're writing some cool, awesome, dynamic website, you can go to the console and debug it from here, or go to the debugger. Really just this whole suite of things is super useful for making your website awesome and even better than it was before. Yeah, and then I mentioned linters earlier. Basically, linters are just programs that just read your program and then tell you what's wrong with them. And they're very powerful. They don't run your program, which is really nice because a lot of times your program will take forever to run or a very long time to run. Or there's like some while loop that just goes on forever. Like it's a daemon that's not ever supposed to like end within a set amount of time. So having a program that just reads through your program and tells you where it's wrong or what's wrong with it can be very useful. The tools for this that I know of are slint for C, Flake 8 for Python, which is sort of a meta package. It includes a few different linters. And this is the output of, I believe, ESLint or JSLint for JavaScript. And it'll give you, most linters will tell you similar things. It'll tell you like, I expected to have a semicolon and instead I got a return statement, and it tells you which line it's on. So you can actually just go to that line and sort of figure out, okay, well, based on the syntax I know for JavaScript, oh, that's what it's missing, okay. And here it'll tell you just straight up on line 415, there's a missing semicolon. So you could probably blindly go to that line and add a semicolon and it would fix the error. And it also tell you things like error is undefined. So it'll actually tell you like this variable is not defined, which is really nice because in my experience, like JavaScript specifically won't tell you, but the linter will tell you. So sometimes things break and the linter is the only tool you have available. There's a pop quiz. What tool would you use to find the missing parentheses? Of course, I'm referencing the title. Paren how to, paren find, paren the missing parentheses, paren. You would probably use a linter to find the missing parentheses because it would tell you expected parentheses on line 1 or something like that. I don't know. I'm trying to make this interactive, guys. Just help me out.
Yeah. To stay on linters. Yeah, so a lot of times your compiler will not actually notice syntax errors, or for particular syntax errors, it's not technically incorrect. It's just something that a linter will notice because it'll be like, hey, so you don't have a semicolon here, and most people put semicolons here. So you should maybe do that unless you really know what you're doing. However, your compiler won't necessarily notice that, and then things will break in really unexpected ways, and it might be hard to find where they're breaking or how. So linters are usually a good like pre-debugging thing to work with. Usually if you're working with any modern language, it'll be pretty built into whatever you're doing. Like Python, you don't really get like your syntax is wrong errors very much. But like I was talking about with C or assembly especially, like those really old low-level kinds of languages, you don't get those nice linty, little messages like, hey, you should do this kind of thing. Things will just break. So yeah, that's why linters are especially useful.
Yeah, as far as the disparity between syntax reporting from the compiler versus a linter, I usually think of the compiler as like a cautious optimist. It usually doesn't tell you like, hey, you goofed, this is wrong. But a linter will just assume you are really dumb, and it'll just tell you like, hey, you did a dumb thing, you should fix it. Mm-hmm. But a compiler is like, yeah, you might know what you're doing. Sure, why not? Straight out. And then your program breaks, and you're like, compiler, please, compiler. Yeah. So style guides are another thing that's enforced by linters. So linters will not only enforce what has to be in a program, like semicolons or curly braces, but it'll also enforce, like I said, say your program needs to have 4-space tabs. So every tab is 4 spaces, or no line can be longer than 80 or 100 lines. It'll enforce that. It'll say this line is longer than what's required. And this is really nice because it makes your code consistent. And in being consistent, it makes it more readable. So if you follow a pretty common set of guidelines, like Flake 8 tends to enforce the like de facto Python readability standards.
Which are PEP 8.
PEP 8, yeah. You can just Google that, PEP 8. I think I might link to it later. You can actually, you end up writing code that if it conforms to what Flake 8 complains about, your code basically looks like all other Python code, or in theory, all other Python code. And that just brings the community together, because anyone who knows Python can read your code, and they don't think like, what are you doing here? What does this code mean here?
Their noob flag doesn't go off.
Yeah, their noob flag doesn't go off. You look like a professional. So anything else? Cool. And going further into style guides is coding standards. So coding standards are very similar to style guides. Style guides might be specific, like a company might have its own style guide, or a project might have its own style guide, but coding standards are pretty consistent among the language. So that's not to say that it's always the case. There are organizations that call it, that they say like, we have our own coding standards. But essentially it's just how to format your code to be consistent with the rest of the code base of the language. So this is a good example from PEP 8 is if you're importing a module or importing a submodule, you say from module import submodule instead of saying import module.submodule. And it just sort of makes readability easier. And this is just standard. So now every time you read code that includes this kind of formatting and not this kind of formatting, you can more or less assume, okay, well, this person knows how to write Python the Pythonic way, or the Python consistent way. Another example of a coding standard or style guide is kernel.org. So the Linux kernel is free and open source, and anyone can use it, anyone can contribute to it. And because anyone can contribute to it, a lot of people that don't quite know how to code might contribute to it. So they have their own style guide, coding style, which just dictates like tabs are 8 spaces. This is how you write functions. This is how you write comments, et cetera, et cetera. And sometimes it's kind of funny. So this is actually a quote from that document, and you should check it out. It's actually a very good model if you want to write your own C code. That is a pretty good standard to write your code against. Another example is NASA's Jet Propulsion Laboratory. They write a lot of code because they send stuff into space, and they have their own style guide, which more or less dictates like, you can read the quote right there. All loops shall have statically determined upper bound on the maximum number of loop iterations. It's very formal, because it's NASA, it's a government organization.
And also they're like dealing with people's lives. Like some of the code they write is literally life or death. Yeah. So they have to be pretty tight with their code. So
they're working with life or death. And if they're not working with life or death, they're working with millions, if not billions of dollars of physical equipment. So, important stuff, pretty reasonable. So they're very formal in their style standards. So moving on, testing is very important. We've talked about testing in the past, but test runners are the programs that run your tests. And they tend to give you some really good debugging information when your tests fail. So it isn't necessarily what a debugger might tell you, which is like, this failed, this is the value, or this, your code stopped working, this is the value of some things when it stopped working. But rather, your code worked, it just produced the wrong answer, and here's the difference between what I was expecting and what I got. So that's a form of debugging, in that you should write your tests, you should write your code to conform to your tests, and your tests will tell you why they're failing. So not quite the same thing, but it is a form of debugging in that it gives you information to make your code better and work functionally, or function properly. Code coverage sort of goes hand in hand with tests. Code coverage is how much of your code is covered by your test suite. So first off, you should just always write tests. Second off, you should always know what your code coverage is. I know if you ever go on GitHub, a lot of big projects will have a little tag that say, percentage code coverage. And you shouldn't necessarily expect 100% coverage, but something like this, 80% is pretty good. Many code coverage tools will actually like highlight these in different colors. So the 80% and above is green, the 60 to 70% is yellow, and everything under that is red, because the color is symbolic of like how good that is as a state of your code base. So moving on to virtual environments. Virtual environments are a Python thing. Essentially, I describe them as a sandbox for Python, but what they do in practice is they wrap up all your dependencies and libraries and put them in a box. What you do is you use the virtual env command to create a virtual env. And this is not to be confused with a virtual machine. This is completely different. They just have very similar names just to confuse us. Whoops. So you create a virtual environment. You source the virtual environment, which means you more or less, quote unquote, enter the virtual environment. And then you are in it because when you're in your virtual environment because you have this little name prepending your prompt. And then anything you do related to Python in that virtual environment, say installing a Python package, is isolated to that virtual environment. So actually, that's really the only thing that's isolated. This is really nice because at some point you can actually just you can export the packages that you have using a command pip freeze. It basically prints out to the screen every package you have installed in that virtual environment. And this is really nice because the packages you have installed on your personal computer might be like some cool tools you found, some games you might have downloaded that were in Python. But what you really want when you're packaging a Python application for the public to use, which is very common, a lot of people do it, it's pretty surprisingly easy. What you want is a list of packages that are only related to that package that you created, a list of dependencies, and virtual environments allow you to do that. So if you have any questions about this, you should look it up, look up the documentation. And yeah, it's a very useful tool. However, it's not perfect. So there's some other ways that other languages deal with dependencies. Node.js creates a node_modules directory, keeps track of your dependencies in a file called package.json, which works more or less. Go does something different, well, similar but different. Essentially, it keeps track of your dependencies in a folder as well. I forget what it's called, some folder name. And it downloads all of your dependencies with Git using the go get command. So dependencies is a very hard problem to solve, and Python deals with it one way. Other organizations, other languages deal with it differently. But if you're going to write Python, you should probably know how it works. And that's one of the first things I look for in a language is how do they deal with dependencies? Because some languages deal with it objectively worse than other languages. One last thing, or almost at the end. This is not a drive of an IDE, but it's a cool video. Basically, an IDE, or an integrated development environment, is a text editor, more or less, that has a bunch of tools built in to help you develop. So say you're like developing an Android app, and you want to use an IDE that you can just click on some buttons, and it just gives you the entire template for an Android application, and you can more or less just fill in the blanks or start writing some actual code instead of having to write out the templates, write out the skeleton code for what you're going to do later. So that's sort of what an IDE does. It also integrates a lot of these tools that we've talked about today. So it'll give you a linter that as you write code, it'll tell you like, hey, you forgot to write a semicolon on that last line. Or you can just press a little picture of a bug and it runs a debugger. Some examples of this include like NetBeans, Visual Studio, Xcode, I believe is the one on Mac operating systems. So yeah, IDEs are very useful. It's up to you. Most IDEs don't provide you anything that you couldn't do in a terminal, but they make it very easy.
IDEs are very useful for really specific things. Like he was talking about Android development, or writing assembly is another thing that is very difficult in the command line. So for stuff like Python, an IDE is probably a little bit bulky and unnecessary. But for something like Android, where you're running your mobile application in your own computer, it might have different behavior than it actually would on a mobile device. An IDE will, you won't have to worry about that with an IDE. It will already have an environment set up. You'll know that it's been very thoroughly tested, that it has all the tools that you need to help you identify any bugs that you run into. and that the final product is more or less what it will actually look like. Or similarly with assembly, it's pretty difficult to like step through assembly code and find bugs. But there are IDEs where you can look at like each individual register and how it changes as your code executes and things like that. So that's mostly why IDEs are in this presentation and what they're used for.
Development servers are basically an isolated, I don't want to say the word server again, but when you're doing development for, say, a web application, you would use a development server to test your application to make sure it actually works, quote, like on the web. So you would put up a server for testing purposes. You might even just spin it up during tests automatically, and it will include test data. It will be super easy to spin up and tear down. And it's very minimal, and it only includes the tools that you need for development and production. So development servers are very nice. They're pretty much just like, they're supposed to look exactly like what production will look like eventually. And there's not a whole lot more I can say about them. They're a thing that you're going to use eventually. But in my experience, you probably won't even think about the fact that you're using them. And today we have an activity. If you go to this URL, you'll find some instructions in the README for how to do some debugging. So the URL is github.com/devopsbootcamp. github.com/devopsbootcamp/bootcamp exercises, bootcamp dash. I'm so bad at this. Okay. github.com/bootcamp. Can you say it?
DevOps bootcamp/bootcamp-exercises/2015-16.
Okay. And then go
click
to,
on debugging.
And then exercise.rst. And
this will just walk you through like a little debugging exercise. So there's kind of two parts to it. One of them is the tiny Flask app that we used earlier when we were talking about web applications. There's a different branch, so that's what the git checkout command is doing. Check that out, and then there's a bug, and you have to fix it. And then the second half of this is talking about linting using Flakegate. So we talked a lot about linting in the last half hour or so. So this is a good chance to look at what it's actually returning and like how it's useful and stuff like that. Get a little bit of experience. So yeah, have fun with that. Please do it or don't. It's really up to you. And thanks for watching.
yeah, thank you.